Thanks. So my talk will be made more or less out of two parts. Okay, for some reason I don't have the table of contents, so I will just tell it. The first part is more mathematical, the second one is more physical. I feel much more comfortable with the first one than with the physical one, mostly because, I mean, in the physical part I will have to tell why it makes sense and what kind of physics we should expect from that. But I mean, I'll pretend that I have something to say about that too. I mean, so the first part, in the first part, I will give some very quick review of relative mathematics, which is used for my further calculations. So essentially, this mathematics is some non-commutative geometry or spectral geometry. Of course, I don't use the full power of non-commutative geometry, but what I will try to argue that independently of very like abstract appearance of this math, it might have some physical applications, and it have had some physical applications even before, and quite powerful. So the general idea, at least for me, behind the constructing non-commutative spectral geometry is the following, that you try to translate some more intuitive geometrical, topological concepts in some algebraic language, which is more abstract, but the advantage of that you are much more open for generalizations, because algebra, more or less, you know how to generalize. So here, a couple of examples. So you have some measure space, for example, sigma finite is some very natural condition. And the classical fact that is the same actually as commutative polynomial algebra. So especially there's some algebra of measures in some sense, dual actually. So it immediately tells you that, okay, now I can define so-called non-commutative measure theory. I just abandon this word commutative and tell that non-commutative algebra defines for me, non-commutative polynomial algebra defines for me some non-commutative measure theory. Of course, you have to tell much more, but essentially the idea is the following, that when algebra becomes commutative, I have to recover my usual measure theory. Another very important example is here. This already more relevant for me. Essentially, this result from 40s due to Gilfan and Nymark, that you can talk either in topological language about locally compact Hausdorff spaces, or actually you can talk about the algebra of functions of those local Hausdorff spaces, which you can easily show that this C-star algebra, commutative C-star algebra. And then you can forget about this space, because this space is uniquely recovered as some space of states, state space, in some natural weak star topology, etc. It does not matter. I mean, I will not use the heavy mathematics. But the point is that this opens up for us the possibility to define non-commutative topology, exactly essentially in the same way. You give up this word, but after that, of course, you want to know what are non-commutative counterparts, algebraic counterparts of usual things that you know in topology, like open set, closed set, map, morphism, homomorphism. So here, just like beginning of the table, you don't have to read or understand much of this table. So just my point is that you can translate everything, essentially what you want. So for example, if algebra non-unital, it will mean that the corresponding topology is not compact, but you can compactify. So the minimal compactification, this one-point compactification, will just amount to minimal unitization. You just add. So C-star algebra is good because, I mean, essentially the minimal unitization is unique. I mean, you cannot just add unity in many different ways. The maximal possible compactification, this stone check compactification, will give for you multiplier algebra, which essentially is the biggest C-star algebra with unity, which admits your original C-star algebra as some non-trivial ideal, and so on and so forth. I mean, so meaning that you can completely redefine your topological structures in the algebraic way. And now it's up to you, in some sense, what to do on this side. I mean, of course, I mean, it should be consistent, but the point is that the most natural, of course, I mean, to take the general C-star algebra, the non-commutative one. That you call non-commutative topology. And after that, you just go ahead and do what you need to do, or what you think you need to do. In the same way, you can go further. You can start putting additional structures in your topological space. You can, of course, natural structure for physics is differential calculus. So that will produce for you another dictionary. I mean, so the point is, this is not a dictionary, dictionary meaning like how you construct this dictionary. You prove this dictionary on the commutative level, and after that, as I said, you forget about one side and start working with another side. I mean, so this is the dictionary more or less for differential calculus, or non-commutative differential calculus. Okay, so you work, you can notice the serious difference between this table and the previous one. So for topology, topology is defined by algebra. So algebra of functions enough to recover topological structures. Differential calculus already requires more. Okay, in Tau, even here you can see that it's not just like some algebra, but this algebra should be realized as some representation in some Hilbert space and all this stuff. And we will see that all ingredients are already important. Again? Algebra, okay. So, but what? Topology, yes, but not geometry. Topology, geometry, different things, right? I mean, so topology, of course, because algebra of continuous functions, of course, I mean, knows everything about open sets, so of course it defines topology. But it's not geometry. Geometry has a lot of different structures. So, for example, algebra of continuous functions does not know anything about differentiability. So clearly, C-star algebra of continuous functions cannot tell you anything about differential structures on your space. Yeah. So that's implementation. I mean. Right. That's my point. That to do that, I mean, of course, you will have to add on the algebraic side. You will have to add more structure on the algebraic side too. Not just algebra, not enough. What any? And commutative manifold. I mean, I will show you the reconstruction theorem, how to reconstruct commutative Riemannian space out of algebraic structure. And just algebra, of course, not enough. I mean. So, for example, you can define integrals. I think Dima was talking about Dixemer trace. Essentially, Dixemer trace is defined on some class of compact operators which have logarithmically divergent trace. So, in any case, you can define your differential geometry. Now you want to go really to geometry, meaning that with distances, so to Riemann geometry. So that was pushed forward to this person, to Kohn, which culminated in this one big book, then another big book, and two big books. And so here is this reconstruction theorem. Here is the complete data which you need to reconstruct Riemann structure. So you need some algebra. Okay, so because you want to reconstruct commutative geometry, this algebra should be commutative. Of course, this will be not C-star algebra, because C-star algebra is algebra of commutative function. It will be pre-C-star algebra, so like C infinity eventually. You need representation of this algebra in some Hilbert space. You need metric, distance. So you start topology, then you put differential structure, then you put on the top of that distance, metric. Differential structure is manifold. So the point is that you cannot discard any of those three ingredients to recover. And here you can, so those things here, these 5 things, I mean, they're very formal, so I will not even talk about them. They look like axioms, but essentially you prove those axioms in the Riemannian case, and after that you postulate them as axioms, as usual. So the point is that if some differential operator, here is the first order condition actually. So it will be differential operator, but here actually it does not say formally that this is differential operator, because I mean it's defined in purely algebraic terms. But after that, when you really will try to represent it, of course it will be just usual Dirac operator to recover usual Riemann geometry. So here, how it works in formula. So let's take, so this guy here is called spectral triple. So this is the basic ingredient of spectral approach to geometry. So let's take algebra C infinity. So this is not C-star algebra, as I said. Okay, in this case we will recover spin manifold or C-spin manifold. I mean. So what I mean this. Hilbert space of sections of spin bundle and usual Dirac operator. So these 3 guys, here I show more or less how to recover some information. For example, distance or metric. So it's just distance essentially between 2 states, because I mean in the commutative case, for the commutative algebra, state essentially is a point. I mean, every point of your space will define a state on the algebra of functions. And you see that Dirac operator enters very non-trivial way. So it restricts the class of the functions over which you take this supremum. I mean, you can, in the Riemannian case, you really prove this formula. How you recover, for example, what is the dimension of a manifold? I mean, you can do it actually in several ways, but the simplest one, this is actually the very old formula from 1918, I think, Weil theorem, essentially. So if you take your Dirac operator, so here, okay, here everything is nice. I mean, this Riemann manifold is compact, because otherwise you should say more things. So anyway, take the Dirac operator, look at the spectrum, start counting states below some cutoff, this counting function. And the Weil theorem essentially tells you how the counting function grows. And the point is that looking at how it grows, immediately you fix the dimension of your manifold. Because, I mean, only for one specific n, this limit will make sense. For any other, if n deviates a little bit one side or another side, it will be immediately either this limit either infinity or 0. Only for one specific n, it will produce for you well-defined answer. And as a bonus, you will also, this is very fancy way how to calculate the volume of compact manifold. I mean, as a bonus. No. For this choice, of course, it will be integer all the time. But I mean, if you, so I will show you that if you mess up with Dirac operator, you can receive some fractional answers too. I mean. So it's called spectral dimension. For nice spaces like Riemann space, it will reproduce exactly. For spaces more singular, they don't talk much to each other. Hausdorff dimension. This has another name, is spectral dimension. So this is exactly this Dixmer trace defines your integration with the correct measure. And this is the object actually which I put in the title of my talk. So this is which will become spectral action. So for the moment it does not, it's not clear why if you look at this side. But if you look at this side, you understand why. So you take very formal thing, Dirac operator. I mean, so for dimensional reasons, you put some scale here. Chi is the cutoff function. It could be step function, could be some smooth function which goes to 0 in some reasonable way. And you start, so here is the like low energy expansion, this heat kernel expansion of this trace. And you see that the first coefficients reproduce, so this is just geometry, so the first coefficients reproduce exactly like cosmological term, Einstein-Hilbert, and high-order terms which look like quantum corrections. I mean, so that was the inspiration for people to think that maybe this has some relation to physics. Of course, I mean, as I said, this is infrared expansion, but I mean, that's what I will need. So what's the motivation to mess up the spectral triple? I mean, so why we are not happy and want to change that spectral triple, the commutative one? So the reconstruction theorem, which I cited, I mean, Kohn proved very complicated theorem that you recover Riemann geometry under those 5 axioms. You recover Riemann geometry from the commutative spectral triple in a unique way. So it's one-to-one correspondence. It's kind of like Gelfand-Naimark theorem, but for Riemann geometry. Okay, so, but I mean, the proof is much more complicated, I mean, at least for me. So anyway, as I said, the generalized spectral triple, generalized meaning that you mess up in some controlled way either of those ingredients, what is generally called non-commutative geometry. Or spectral geometry, because I mean, as you can see, the spectrum of the operator, relevant operator, is very important. So here, just a little bit of physics. I mean, to start the physics, I would say. The point, the ideology behind all of this is the following: we want a single operator, or the spectral triple, let's say, to define everything, not just geometry, but also physics. So in some sense, we want to build the physics in a very unified geometrical way. Not just geometrical part of physics, but also the meta part of physics. After some motivations, of course, it's done in some axiomatic or the way through postulates, essentially. And you check the postulates, give consistent answers for some known cases. So how it works? So you start with this Dirac operator, whatever object you call Dirac operator. You construct the geometrical part of your physics exactly through the spectral action of this type. So that simultaneously will produce for you space-time, like your geometry, and gauge. I will comment very quickly that actually in this picture, in this approach to standard model, Higgs takes very nice place actually on this side, in geometrical side. So because if you look at the standard model, you have gauge fields which are connections on some fiber bundles. You have matter fields which are section of fiber bundles. You have Higgs, and you're not very clear where to put it geometrically. So here it belongs here. You can show that infrared physics does not depend much on it. It enters, chi enters here through the coefficients, this F0, F2, there's some momento of this function. So it's 3 parameters, essentially. And the higher energy physics will be suppressed by this scale, 1/, so that you're free to put like quantum scale, quantum gravity scale or something like that. And matter part essentially is the Dirac action. But the point is that this is the same Dirac operator. So examples. As I showed you, this commutative spectral triple. So here you put some more information if you need to have more structure, if you need to have complex structure, if you have if you want to have some let's say chirality and all the stuff. Still it's called spectral triple. After those, is some Z2 gradient. It does not exist for any dimension. But anyway, so this is one example of spectral triple. It produces, as I showed you briefly, the usual geometry, just geometry. The probably simplest example is finite matrix geometry. Just take algebra of matrices, finite matrices. Hilbert space is pretty clear what is Hilbert space. Dirac operator is some matrix. You pick some Hermitian matrix and call it Dirac operator, and so on and so forth. But the interesting thing that the combination, so-called AC geometry, almost commutative geometry, the combination of these two spectral triples, this is exactly after proving some facts that actually you don't have that much freedom here. If you want to have some consistency, there's some. What do you mean? You have discrete group in your system, acting on space or what? Okay. So it should be represented on algebra. So meaning that the algebra will you remember that this is algebra of functions on your space originally. So it will of functions on your space. So it will be represented somehow on the algebra. It should be distance. It defines your distance. Yeah. Because I showed you here. 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 It enters here in the condition of what functions are allowed to take this supremum, and you can prove that if it's Riemann geometry, this is exactly this kind of Lipschitz distance, I think. So this is exactly produces the metric distance. So meaning that messing up with Dirac operator, I will mess up with this condition. I will admit more or less function here for this supremum, and I will move my distance away from the Riemannian distance. No, you can, but you will change the geometry. Yeah, you can, but once again, you will end up with completely different geometry. So that's the point. So if you want to recover the Riemann geometry, the original one, yeah, so here, but that's my point. So if I want to recover the Riemann geometry, the original one, Riemann geometry for which this Dirac operator was written, because you see there's a spin connection. So if I want to recover now this Riemann geometry in purely algebraic language, so here I don't have anything about geometry. So I have some differential, first order differential operator, first order condition was some like second axiom. Yeah, should be commuting and all this stuff with some. No, no. It's like for velocity. So so if you change this condition, you change the notion of geodesic. I mean, so different things will be geodesics, and so you change the geometry. You have to mess up Dirac operator. I will do that. Yes, yeah. Yeah, uh-huh. Yeah. I hope I will do that. So anyway, very quickly, because I mean, this is not what I want to talk about. I mean, so this almost commutative geometry is all you need. I mean, all you need after almost 20 years of work of the group of people to reconstruct in this approach standard model. So once again, because this is not the topic of my talk, I mean, so here, more or less, module many other words, I mean, this is finite geometry. You see this finite geometry more or less reflects your gauge symmetry, right? U1 cross SU2 cross SU3. I mean, so here is your Hilbert space, which of course, I mean, you put there by hand, knowing the matter content of your theory. I mean, so you just essentially just direct sum of all needed Hilbert space for fermionic states. So the remaining operators, as usual, some charge conjugation, chirality, and all this stuff. I mean, and Dirac operator is here. Essentially, you put the usual Dirac operator of this type, plus fluctuations. So those fluctuations, what will become gauge fields. And after that, you just take this trace. So because you're interested in infrared, I mean, so you do this heat kernel extension. Okay, so expansion, so I did not write. But the point is that you will recover exactly this guy, so this, for example, first two terms, I mean, so if you need to go further, I mean, you can produce some like corrections. But the point is that, of course, you understand that you will reproduce, actually in this order, you will reproduce F squared term. Jan Mills, you will reproduce all this stuff. I mean, so you will reproduce Jan Mills coupled to gravity in minimal way, and this part of action, matter part of action, of course, will produce matter sector of standard model. After that, you start fighting for details, but this is the basic idea. And because, I mean, it's purely geometrical, it produces some predictions. So I'm not a big specialist in phenology. I'm not a specialist in phenology, in numbers and all that stuff, but it produced some predictions, so like relation between masses on classical level, unfortunately. So, but anyway, this model reduces the parameter space. After that, you should understand what does it mean, how to take it to quantum level. We will not do that, so we can talk afterwards. So anyway, so what is my motivation to apply this machinery? Of course, quantum gravity. So we heard a lot of that during this workshop. So every person has his own favorite motivation, one to consider quantum gravity. So this is the standard one, that means perturbably normalizable. You would like to look for some kind of UV completion, one way or another. So string theory provides some UV completion in non-field theoretic ways. I mean, it completes in strings, so gravity emerges as some effective thing. Some loop quantum gravity, pick your favorite. So the one of the basics, basic motivation, I think Dmitry Vasilievich, Dima Vasilievich mentioned that essentially, if you stay in classical gravity and try to make operational meaning of points, because I mean classical gravity is defined on differential manifold, and so you have to say that how do you define a point of manifold? You start measuring. If you start measuring the point on manifold with better and better precision, you start creating black holes, and you don't know what does it mean. So it's a clear argument that I mean somehow on Planck scale or whatever you call quantum gravity scale, the geometry or approach should be modified. Call it quantized. So this is the main motivation for me. So Harava looked for UV completion without leaving the field theory. Okay, so he wanted to look for some completion within field theory. And he used very old idea of Lifshitz. This was in condensed matter, I think. The idea was the following. So let's consider this simple model. So just to demonstrate the idea. Okay, so you have two scales. So you have UV scale and actually UV in infrared. So how you can see that? I mean, so fundamental, of course. I mean, is this one, but you have to assign some non-standard scalings, the units for x and time. So you see this essentially non-relativistic. So time and space, they scale differently. So how do you can see that you have two regimes, two fixed points, more or less. I mean, so consider this free theory. So consider the propagator, and then you can develop two perturbation theories essentially. I mean, so one perturbation theory, when energy very large, you can think that this term is very small, and kind of like you see, this guy will be producing vortices. And so with fundamental propagator being non-relativistic one. In infrared, and infrared exactly is dictated by the relation between those two parameters. I mean, so essentially it means that this term is small. You do another kind of perturbation theory. So you see that this theory is relativistic or looks like relativistic in infrared, not in ultraviolet. So fundamental theory, fundamental symmetry is actually non-relativistic one. So he just applied this idea, he being Harzawa, to gravity. So why? Here is some preliminary argument. I think Shiko was telling about this. So we will have to break Lorentz symmetry. I mean, why? Because I mean, if I just will start adding more derivatives, I will start producing problems. Okay, so problems, of course, come from more derivatives with respect to time. And actually, it's not something new. It's actually related to this Ostogradsky ghost from 19th century in differential equations. I mean. So you don't want that. Because, I mean, of course, we know that perturbatively renormalizable gravity exists from 70s, no? Stelly did it. So if you add some in controlled way R squared terms, it's renormalizable perturbatively, but I mean, it's problematic. It's not unitary. So you want to make it both renormalizable plus good. So essentially, the idea is the following. Time is preferred. So you don't have to do much. You do the usual ADM slicing. Okay, you do foliation of your space-time. So here is the usual Einstein-Hilbert action. Of course, now everything is controlled by 3 geometry, and the way how this 3 geometry is embedded in 4 geometry. There's some extrinsic curvature here. And after that, you start saying the following, that this slicing structure, the foliation structure, is fundamental. Because, I mean, here in this approach, in the canonical approach to gravity, actually you will see that this is like essentially theory still remains not essentially this four-dimensional diffuse, because you have some constraints and all this stuff which ensure that you have symmetry, four-dimensional symmetry. No, because this is exactly four-dimensional curvature. This, yes, is R. So the point is that each coefficient here is crucial, meaning to combine this into four-dimensional R. If you mess up any of those coefficients, immediately you will break four-dimensional diffuse, meaning that you will obtain object here which will be not scalar with respect to four-dimensional diffuse. So that's the idea of Hajava. Let's do that, I mean. So let's do that, meaning that let's think that fundamental symmetry is not four-dimensional diffuse, but foliation preserving diffuse. So I'm allowed to do only such change of coordinates which preserves my foliation structure. So that's exactly this. This one. Okay? And after that, you do a la Lifshitz. You try to prescribe some anisotropic scaling between space and time. In which way? In such a way that actually in theory you have enough of space derivatives. So you see, you don't introduce more time derivatives. You introduce more space derivatives, which improves convergence. But from the dimension analysis, you can understand how many much derivatives on space you have to introduce. Actually, it should be 3 derivatives, actually 6 in action. It means the following. If you remember the extrinsic curvature, the second fundamental form, it looks like velocity, right? I mean, it's the only geometrical object which depends on time derivative. So you want to keep that quadratic here. But now I can put here whatever coefficient, actually, because I mean, each term separately is 3D invariant. And here's some potential where I include terms up to 6 derivatives, so up to R cubed in 3-dimensional curvature. Okay, and you can argue, at least initially it was just by counting that, I mean, it should be renormalizable, but recently there are some works by Barvinsky, blah, that argue, okay, let's say, that make some statements about the actual consistency, quantum consistency of this theory. There are 2 approaches. Actually, you can show that there are sectors. You can think either this lapse function is purely depends on time, because I mean foliation preserving diffuse organized in such a way that it will remain depend only on time. So this so-called projected gravity. Very quickly, I mean almost immediately, people realize that it's quite impossible to confront with the experiment, even within the solar system. So, and next year, this group of people, they show that actually non-projective gravity can be actually, can make sense up to the following fact, that I mean, it has like up to 100 coefficients, parameters. With 100 parameters, I can fit almost anything. So my motivation was, the primary motivation was, can we suggest some guiding principle to restrict this number, this parameter space? Plus, on the top of this, actually, there is a problem how to couple this to matter. I mean, so here, quickly some properties that, of course, it will lead to some, because it breaks for diffuse, strictly speaking, should lead to Lorentz violation. So this is my motivation. So a lot of free parameters. So how to couple to matter, meaning that, strictly speaking, now you have to couple to matter also in this foliation preserving way. There were immediately works which showed that it will introduce so much of Lorentz violation that actually you have to stick to coupling to the usual geometry, which is very non-natural. So you have geometry which is actually not 4-dimensional diff invariant, and you couple matter as nothing would have happened. So I will be mostly showing results for this infrared limit, meaning the infrared limit, essentially, you drop all these terms which lead to renormalizability, and you just stick to the usual action, but here, those are parameters, so it's 3-parameter space. Okay. So here, I doubt that I will be able to show, or at least flash all the results. So here, how this apparatus of the first part of the talk could be applied to analyze these models. So the question is the following. So what is the actual physical dimension of this theory? So very quickly people got suspicious that maybe the physics does not see all the 4 dimensions, and actually it's, in ultraviolet it's lower dimensional effectively theory. Harava showed through some model calculation that yes, I mean, it seems that it looks like 2-dimensional in ultraviolet. So what does it mean is the following, that physics, as I showed in this approach, in the approach that I'm advocating, is defined by Dirac operator. It's some physical operator. So spectrum of this operator essentially should tell us everything in some sense. So let us see the spectral growth, how this spectrum grows. So that's how, in some sense, we would measure the dimension. We would measure some spectra and deduce from that the conclusion, our conclusion that the dimension is like that. I mean, so essentially, first we did some model calculation. So this is like Dirac operator up to 3 derivatives. I mean, it's some schematic in flat space-time. And for this, you can calculate, of course, spectrum. And so here's some calculation. Thanks. So the point is the following. Why? Of course, I can continue to use the usual Dirac operator, this 4-dimensional, but then the geometry which I will reconstruct will forget completely about the foliation structure. I want to put some Dirac operator such that will respect this foliation structure. So essentially, if I break now Dirac operator in 2 parts, like Dirac operator, roughly speaking, along the time direction and 3-dimensional Dirac operator, that guy will remember, and the geometry, whichever geometry I will reproduce, should remember about this fundamental structure. And I want to construct a physics which knows about this foliation structure. So that's the connection. So this Dirac operator is the example. So you have time derivative, this usual. So the first term plus last term is the usual Dirac operator, essentially. And here, more derivatives. So it's this schematic expression. But if you do, you can do actually for this case the calculation, and you really can show that in infrared meaning that cutoff being below the scale which is introduced by the coefficients here. If this cutoff is well below this scale, the spectrum will grow as for 4-dimensional Dirac operator. If the scale is well above the Dirac operator, the spectrum will start looking more and more like 2-dimensional. Yeah, so this is just to test whether this works, the geometrical part. I mean. So Harava-Lifshitz gravity, essentially, of course, I want to take this Dirac operator which works for me, take the spectral action and show that Harava-Lifshitz gravity here. So this is infrared Harava-Lifshitz gravity. So I want to argue, probably in last 15 minutes, that the natural Dirac operator, which respects foliation, the trace, the spectral action built out of that Dirac operator, will reproduce exactly this action. So in infrared, only this term will control but in ultraviolet, term with more derivatives will start dominating. This term will. So here I put the same scale, but I mean those, strictly speaking, all arbitrary parameters. I mean, so the parameter in front of the higher derivative controls the.
This is maximum, most general format somewhat.
No, this is most general for flat space. I mean, so, but the point is because the ultraviolet dimension, of course, I mean, you understand that it's very local. I mean, so flat space, not, but I mean, here's the calculation. No, the result, actually, you can use the whole machinery of spectral geometry to prove that ultraviolet dimension will be 2 for any curve, not curved. So for that, you just used some generalized zeta function. And for that, you don't need the details of the coefficients in front of intermediate derivatives. You need only the behavior of the principal symbol. So what you do essentially, because you have foliation naturally leads to some integrable subbundle in tangent space, and the existence of integral subbundle in tangent space allows you to introduce some natural filtration, meaning that you call one of the tangent vectors having order 1 and the perpendicular order 3 here, for example. And that tells you that in the principal symbol, to compensate one time derivative, I need to include 3 space derivatives, so for principal symbol of the Dirac operator. And knowing the principal symbol, you can prove the quite general theorem that the poles of this function, general zeta function, have this form, where z is exactly this scaling, the anisotropic scaling. So the first pole, strictly speaking, this is called so-called, strictly speaking, this controls the different type of dimension. It's called analytical dimension. But there is some Cohen theorem that for nice spaces, analytical and spectral dimension is same thing, because analytical dimension is controlled by some residue. So, and you can see that from here, looking at this formula, you can quickly derive this dimension. And you see that when this number, the dimension of the foliation, 3, z equals 3, 1 plus 1 is 2. But I mean, using this approach, because it's based on the analytic continuation to the meromorphic function on the whole plane, of course, it does not allow you to tell anything about how this transition from 4 to 2 happens. I mean, it tells you only that, okay, for sure, in ultraviolet, it will grow as two-dimensional spectrum. Yeah, so we did it, but only for very specific case. For flat case, we have analytic answer. So here, so my point is the following. Even for flat case, the answer is so ugly. I mean, it uses some Fox function, which is generalized hypergeometric function. So it's not generalized, you have to generalize that one. But the point is that a lot of properties are known, and here you can, for the spectral dimension, you can have the closed answer. So to visualize, it shows how it goes from ultraviolet to infrared. The dimension grows from 2 to 4. And here some characteristic scale is controlled exactly by the coefficient. So this is coefficient in front of the higher derivative. You know. Oh, where? This heat kernel. This, yeah. So heat kernel allows you to define the dimensions. Essentially, yeah. No, that's true. The point is that the question is, you have to calculate heat kernel for what? What the yeah. For this, yes. No, for the spectral dimension, of course. For the action, of course, you have to be more careful, because I mean, for example, matter part of the action is really the diagonal element of Dirac operator. Oh, it's very easy. I mean, Dirac equation is completely different from Klein-Gordon. So no. No, right. So for some calculations, square of Dirac operator, of course, is enough. For geometry, for this heat kernel calculation, d squared actually, that's what we use. I mean, but for other, so there are many stories and sub-stories here. So this is just one sample calculation. I mean, so of course, I mean d squared, because I mean it depends only on spectrum. So if I know the spectrum, so of course I can recover the spectral growth. So in Weil theorem, it will just tell you either I use d or d over 2, where d is the dimension. I mean, so that's the only difference. I mean, but anyway, so answering Amilka's question, so this is the result, analytical result that really you have. So this is not quantum flow dimension. This is really classical flow of spectral dimension. I mean, so that's how classical physics, in some sense, would see the dimension if we do experiment with better and better resolution. I mean, so if we start with some poor resolution, we will see 4 dimensions, better. We will see more and more spectrum, and we will see that, okay, the spectrum starts deviating from the usual 4-dimensional behavior and starts behaving more and more like in 2 dimensions. So matter part, so I have like 7 minutes for matter part. So as I said, in this approach, coupling matter to the in the usual way. So usually right now you have Harrow ellipses plus completely undeformed matter part. I mean, undeformed meaning that it's unusual coupled to the usual metric. So in this approach, because as I said, Dirac operator defines the metric. This coupling of matter to gravity looks like minimal. Not looks like it. This is analog of minimal coupling, because I mean that's exactly minimal coupling. So meaning that if I use the usual matter with undeformed geometry, so meaning that here I have to put not my Dirac operator which respects foliation, preserving diffuse, but the usual Dirac operator from the Riemannian manifold, which is not equal to the original one. And it will mean that actually this is not minimal coupling. Okay, it will mean the following: that so this is generalized Dirac operator, for example. This is Riemannian Dirac operator. There is, let's call it some difference. So if I couple to this one, it will be something minimal coupling plus non-minimal term. Yeah. So it's really an integral over spinors and all that stuff. I mean, so, but the point is that this is really not minimal coupling. I mean, so if I couple to another Dirac operator, to another geometry, it's not minimal coupling. So, but as I said, the problem is, of course, the huge Lorentz violation immediately. I mean, so even on the level of the geodesic motion, so probably it will be last thing which I explain, and the rest I will just tell in words what could be done else. I mean, because if I have this kind of coupling, I have to redefine, I have to understand what is my geodesic motion, because I mean, the fact that in general relativity particle, pointless particle, structureless particle of mass m follows geodesics, it's not a trivial fact, right? I mean, so that fact is completely based on the energy, covariant energy conservation. So if you don't have that, you don't have the fact that physical motion of point particle follows geometrical geodesics. Okay, this result due to Dixon, actually due to Einstein, but Dixon after that did a lot of consideration. The point is that if I couple in this way, of course I break this 4-dimensional difference, of course I don't have covariant conservation of energy momentum tensor, but I have rather the projection on foliation only being preserved. I mean. So it means that after you do calculation of your physical motion in whatever way you like, I mean, so here that I will skip, I just give the result. I mean, that if you do some analysis how the point particle moves, you will see that actually it does not move along geodesics of the original geometry, but it does move along the geodesics defined with respect to this deformed Dirac operator. You remember that I defined what is the geodesical distance in if my geometry is defined by Dirac operator, and it was some formula. So the point is that point particle after this coupling, and it's quite natural, it's like additional force here. Point particle will not follow the geodesics of geometry, this Riemannian geometry. I mean, I still can put the usual Riemannian geometry. No, because that's how you couple in the usual way. But it will follow some deviated geodesics, which is still geodesics of the generalized geometry. In some sense, you do have this equivalence principle. I mean, so this is essentially equivalence principle, right? I mean, that the particles follow geodesics equivalence principle. And so this is what I will flash. I mean, so that's answering your question. I mean, so this is the infrared limit of Horowitz's gravity. So I take, and this is partially answers your question, Daniel, also. I mean, so we put some terms which are odd. So this one and this one with gamma 0 here. Actually, those terms for us were very crucial because if you don't include, so we don't understand completely, if you don't include these two terms in the Dirac operator, you don't reproduce Horowitz's limit. I mean, so, because I mean, for the usual four-dimensional Dirac operator, only this term you have, and C3, this one. So only these three terms will contribute to with this specific coefficients. This is 3+1 decomposition of Dirac operator. So clearly, what does it mean that now we have to construct most general Dirac operator, still first order, and with arbitrary coefficients in front of all these 3+1 decomposition. So clearly it will respect this 3+1 symmetry. So plug that into this spectral action, and what you will do, so here it's very, very clear. The comment, so yeah, I'm finishing. The comment is that the particle will effectively move in some effective metric. I mean, so this is the usual, when this is 1, this is the usual metric for foliation, So it will be the space part, the space distance will be rescaled in some sense. It will be moving along the space direction slightly different than along the time direction. So here's the answer. If I use this Dirac operator in the spectral action, I will reproduce exactly this guy where the coefficients here, these coefficients, are controlled by the coefficients in the Dirac operator. So here relation, the advantage, so this I will tell just in words. The advantage of this approach is the following, that now, if I insist that matter couples through the same Dirac operator, of course, I mean, the same coefficients, the C1, C2, C3, enter with, as Lorentz violating parameters. The gravity, as was yesterday mentioned, the gravity, for example, this post-Newtonian parameter beta, is restricted, but it's not restricted that much. It's like 10 to the minus 4, something like that. So gravity restrictions on deviations from general relativity not that strong. On the other side, the restrictions on the Lorentz violated parameters, they're like 10 to the minus 15 to 30, very, very strong. So if I insist that the same Dirac operator participates on both sides, I can use the Lorentz violating, the experiments which restrict Lorentz violated parameters to put restrictions on the parameters in Horowitz's gravity. That automatically will require that they should be very, very tiny, the deviations from the general relativity. And that will make peace for people who don't know how to do that, because I mean, they know that they should be small. Really just like to explain that Earth goes around the sun as the way it goes. I mean, so spectral action could be like a mechanism. It's not clear why this mechanism should be implemented, but I mean, if you insist, then you can use experiments on gravity sides, like to put some restrictions on Lorentz violating parameters if you don't have some experiments for that. But actually, for me, it better works. Lorentz, the absence of Lorentz violation almost insists that you don't have violation on gravity side either. I mean, so if Harava-Lifshitz is true, it should be very, very fine-tuned in some sense. I mean, so probably through the spectral action. Okay, thanks.